Okay, so let's get started. Welcome everyone at today's panel focusing on programmable cryptography. We have with us several great panelists that are definitely pushing the boundaries of the research and applications when it comes to Web3. And with that, I would like to hand over to each one of them to just briefly introduce what are you doing and what part of the project you are actually actively involved in. Okay, we can start with DC.
Awesome. Hello, hello. Yeah. So I go by DC Builder. I'm a research engineer at the Worldcoin Foundation, where I mostly work on applied cryptography and blockchain engineering. Yeah. Um,
Thank you. My name is Omer. I'm CEO of Ingonyama. We work at the intersection of hardware and cryptography. And usually the interesting cryptography for us is this ultra-modern cryptography, also known as programmable cryptography. And so this is our focus.
Hey, I'm Morten. I'm the director at Zama, a company focused on fully homomorphic encryption, and also now building this into blockchains.
Okay, perfect. Thank you. So I think we can dive into the follow-up question. That is goes if you could provide a bit more details actually when it comes to how you envision and actually you are using the programmable cryptography inside of your project. Maybe starting with DC.
yeah. So I would first like to start with like a general description of what sort of types of programmable cryptography there are in this space. So the main categories would be zero-knowledge cryptography, multi-party computation, fully homomorphic encryption, and depends if you can or not trusted execution environments. So essentially, at WorldCoin, we leverage a bunch of these different primitives. For example, the way that you prove, so an introduction about WorldCoin, right? So in WorldCoin, it's a way that we are essentially building a privacy-preserving proof of personhood protocol. And what that means is that we verify humans using this hardware device called an orb. And the orb is able to take a high-resolution image of the person's irises. It's able to check that the person is, first of all, like a real human being. It does this by a bunch of anomaly detection models. It checks that you have a 3D face, continuous heat map, that you're not wearing contact lenses, glasses, etc. And after that, it computes a unique representation of your irises called an iris code. And this one just essentially represents how unique a person is. Because you can encode the randomness of it. You can compare people against each other in a privacy-preserving way. And once you compute that a person is unique, you insert a person's public key into the set of verified users, which is a Merkle tree. And then leveraging zero-knowledge cryptography, you're able to prove that you own a private key to a public key in the set of verified users without revealing which one you are. This protocol is called Semaphore. It was built by the Ethereum Foundation, the Privacy Scaling Exploration Group. And yeah, also we're using multi-party computation for the iris code sort of uniqueness check in and of itself. So when you're doing this comparisons of vectors or like iris codes against each other, the way that it worked before is that you have a database in plain text of all the iris codes, and you checked like linearly, you do a linear search of iris codes in the database, and you compare them against each other, and you check this distance between them. So now the way that it works is that the database itself is split into MPC shards, and you're able to compute uniqueness in a way where the database is never revealed in plain text. It's always in this ciphertext or linear secret sharing space. And yeah, so those are like the two main use cases of ZK. And there's plenty of others, but I want to give the opportunity to other members to speak about theirs.
Right. So this here defined in a way this family of cryptographic protocols, multi-party computation, fully homomorphic encryption, zero-knowledge proofs. There are probably a bunch of others, and also a way to compose them into meaningful protocols and programs, applications. The way that, or at least where we start as a company, is the lowest possible level, which is the hardware. And we've been building this toolbox, including hardware and software and algorithms, to basically solve these computational problems that may arise in the context of this type of cryptography. Now, while we started the hardware, we do need to be minded to the actual applications. I think that in general, the more specific you can be, the better it is, right? The better solution you can actually tailor to a problem. So I'm finding myself, I just gave a talk on gaming and ZK and NPC, for example, multiplayer gaming. how to get cryptography to play part in solving cheating for AAA games like real-time strategy games. And now we are talking here at an AI event. So I'm finding myself talking finding myself in different verticals, wherever we can apply cryptography and try to walk my way all the way down to the bottom and see what's the best way in which we can actually build such a solution that would scale and would be efficient enough to be used in a real-world scenario.
Yep. So what we do is we're a cryptographic company at the core. So we develop a fully homomorphic encryption library that runs on CPUs, GPUs, custom hardware. And then on top of this library, we're doing integrations, one into blockchain and one into machine learning. And what we're finding there is how do we make this cryptography that we also as a research company spend a lot of time making user-friendly, developer-friendly. How do we expose this to developer in a way where they can reason about this, where they understand what's going on, where they can control the leakage that's involved in this, and basically making it accessible, which also includes not trying to mess too much with the tools, but use some of the tools that already exist out there to make this a good experience.
Great, thank you very much. Just kind of a follow-up question in a similar direction, so we can currently see where we are. It will be also interesting, I think, for the audience to see where do you plan to be maybe in the next couple of years. Where do you see the challenges when it comes to making your solutions more usable, but also kind of general aspects of general adoption as well for your particular needs?
So to me, like it always comes to like multiple facets, right? Like if you want to make this more performant and easier to build with, you need to build better developer experiences. Right now, we're like in the middle of the adoption curve, I would say. There's already enough interest for ZK or programmable cryptography to the point where people have heard about it. People know what it is. It's not a niche research paper like it was back in 2018 or 2019 or 2020. We already have tools that people can use without having knowledge of cryptography, but there's still some things that you need to learn around it. So essentially, we need to create abstractions that make it very seamless for the average developer to build an application that does some form of programmable cryptography. You're already seeing this with things like zero-knowledge virtual machines, right? Like you just write a program in Rust, you compile it to RISC-V, and you create a ZK proof of that because you have a ZK virtual machine that is able to make a proofs about the RISC-V virtual machine execution. So essentially anything that makes it so that developers can use their existing set of tools instead of having to learn cryptography or learn special languages for writing these sorts of things, be that FHE, be that MPC, be that ZK. This will make it a lot more accessible. And also the cost to reward ratio needs to make it economically feasible, right? Like I, as a developer, will not pay $100,000 to create a zero-knowledge proof or to do an MPC thing for an application that is a game between my 3 friends that have $10 in their bank account, right? Like there's no point there. So you need to make it economically feasible, so it needs to be cheap enough to actually run it on either like consumer hardware so that people don't need to trust servers or people can just have it as part of their daily thing. And that's in general like where it needs to go, in my opinion.
So first, when I checked ChatGPT before, whoever I asked who coined the term programmable cryptography, and apparently ChatGPT identified Gapship as the first, or at least the one who coined it. So Gapship is this dev, is really brilliant. He came up with this interesting game that includes fog of war and runs on blockchain. Now, the reason I'm saying that is that this is the kind of experiences that I expect to see more and more happening. So in a way, modern cryptography, as we are familiar with, which is running in our infrastructure, in the infrastructure of the internet, this is encryption and digital signatures. This is also, this is kind of like the boring cryptography, right? But where we are heading, what we are trying to, when we try to look into the future, is basically building the new internet based on this type of experiences. Web3 is this expanding thing, right? It's like growing by way of removing decentralization, removing centralized authorities by adding privacy, which has become more and more important. So I just think, and this internet is basically, this new internet, this new Web3, whatever, is actually going to be based on programmable cryptography. So the tools that we are now building, right, that the teams at WorldCoin, Zama, what we are seeing, experiences that the developers like Upship worked on, this is kind of like the building blocks for this new kind of internet, and programmable crypto is what's going to run like at the bottom.
I think the kind of the path we took to get here is interesting. So in cryptography, you typically start out with a custom solution. So you develop specific primitives, and then you build a custom solution around that. And then at some point, you realize this requires a PhD in cryptography to use the tools. So you end up making more generally available generic platforms. Like you build this into a programming language. We have examples where you code in a normal programming language, and then that gets transpiled into a language that runs on encrypted data. Which is useful, but then I think there's another step after that, which is you realize, okay, now we have this general purpose platform for secure computation, but we can actually make it a bit faster if we tailor it to the application. So we kind of come back a bit and we say, okay, but instead of using a general purpose framework for secure computation, how about we make a framework for encrypted machine learning, for instance, and then we specialize it for that, or the same for blockchain. One example that we have is that we have a general purpose library, TF8GRS, but we see applications from blockchain saying, well, it could be nice to do this. We were just talking backstage about this kind of private information retrieval or looking up at a table of encrypted data. If you can do that natively or or naively in any general purpose language, but it becomes very expensive. So you want to have some kind of specific primitives for this. But I think this back and forth is interesting, where you can make a general purpose, but you lose a lot of performance, which is the key to your point as well about cost here, right? But then you kind of go backwards a bit and say, okay, what are we actually using this for? The other point I wanted to make is I think there's also something that comes after. So even if we have a general purpose language and we try to abstract all these things away where developers, they don't have to have a PhD in cryptography to use the tools, there's still something that's inherent, right? There's still this idea that maybe so speaking in the Zama context where we have confidential computations, or computing on encrypted data, the developer will sometimes still leak something. They will still have to make a choice. One example could be that you can do an encrypted transfer, ERC20 transfer, and then you want to check if you have sufficient funding in the account. Well, the typical approach would be that even if the balance is encrypted, in order to do the check to see if you have sufficient funding, you might choose to decrypt this Boolean value and then only leak this. But this leaks something as well. So from a developer perspective, you still have to think about, am I leaking too much? And this is really application specific. So there is something the developer has to learn. We can take all these abstractions, we can help them and so on, but there is an inherent leakage that I think is independent of using secure enclaves, MPC, polymorphic encryption, and so on. And we can't get around this. And I could see a next step on the line is to develop some tools for the developer that helps detect these leakages. We've seen again and again that even advanced experienced users of a framework will, at some point when the application is complex enough, leak something that they didn't really intend to leak. So having some tools that can look at this and say, do you really want to leak this thing here? I think that could be useful.
I think in all of the answers we touched on the aspects that I think is also very interesting from the perspective of being currently at a university where actually we are educating the next generation of Web3 native developers. That currently we see that we are actually maybe living in a domain where we go to a conference that is focused on Web3. Many people actually understand a lot of the terms, but when you go back to university or talk with regular people and developers, they don't have necessarily the necessary experience in knowing what all of these tools can provide. Maybe I would like to hear your take on how is your experience when it comes to presenting such complex solutions that you are trying to build to general developers, but also maybe reflecting on the aspect of how can maybe educational institutions help in educating the next generation developers for which such complex systems will be presented in a sufficiently enough detail that they will understand what's going on different aspects.
Yeah, I mean, this is something that is really hard to do systematically. Usually on the academia front, you just have to be really lucky that your PhD advisor is someone who is knowledgeable about the state of the art of things. I think something that can bridge the gap here is just LLMs, right? Like things like Perplexity that allows you to search the internet and then use an LLM to process information. It's really helpful. For example, that's what I use when let's say there's a new cryptographic paper like Binius, and I'm like, okay, what is Binius? What is a binary tower of fields, whatever? What is this cryptography thing? Like, it searches the paper and it summarizes it, and then I can maybe ask my PhD advisor to actually explain the cryptography behind it in more detail or whatever. But I feel like this is something that can bridge the gap and scale because there's just too many things happening. It's not even the professor's fault. Like they grew up something and like they were, at the time when they were able to process so much information, they were like 20, 30, now they're in their 60s. So it's hard for them to process new stuff or to assimilate it as fast as it's happening. So yeah, I mean, the way that I use to explain these things is that I give some naive notions of what it does and what they can use it for, and demonstrate use cases. And then they get hooked, and then they can go down the rabbit hole on their own with an LLM or with the aid of their professor or friends or peers or coworkers, whatever they may be. But yeah, that's like usually the approach that I take in explaining these things.
So my approach is 3 parts. One, I definitely think that the relationship between academia and industry in this particular area are super important. And now the question is, how do we define them? What needs to happen? Who works on what? Because the boundaries, specifically also with blockchain, we've seen it time and time again, how the industry is moving at such a speed that like makes academia kind of not really effective. But it's not true. I do believe that there is a lot of like academic work that needs to happen, and maybe it's our responsibility as industry to provide tools for people in academia to build with. One thing that people say about NVIDIA and the reason why they are successful is because they came up with this CUDA language, right, to build AI applications. Now, when someone going to build the new like LLM or some kind of like new AI next generation, it's probably going to be compatible with CUDA. Like they at NVIDIA gave you the building blocks so that this is how now you imagine, this is how you think about AI. And I think we can do the same. I mean, that's part of what we are doing, which is building tools, building libraries that can be used as an infrastructure and can be used in academia, and then do the extra like steps needed to actually make sure that it reaches the people at academia, work with professors and with their teams to make sure this is actually being used. And the last part is the open source. So this is something we take as granted for some reason, but it's not the case. Like it's a feature of our industry, cryptography in general, and obviously programmable cryptography should be kept open source, patent-free. That's the way to move forward, and that's the way for like having this collaborative environment that would also help with education. You can see the code. You don't need to kind of like guess. It's not behind walls. It's not one company that has a moat. It's like, it's out there.
I think even internally in the company, there's sometimes some tricky parts here where you want to have software engineers talk to cryptographers and speak in the same terms. Even I think thinking in some of these things that you can't abstract away. One would be, as we talked about before, like information leakage. The other one would be security models or threat modeling of the system. You mentioned about MPC. Well, there's so many different MPC protocols, and they all have different security properties, thresholds, and so on and so on. So there is some vocabulary and terminology that you need to communicate even within a group of engineers. So I think education is one way. We can abstract some of it away. I think the technology is interesting from an academic perspective as well. In my experience, academics would like to have these use cases. So if you come with them and you say, okay, but we actually have a real world use case, that they really want to get involved in that. But yeah, there's still work to be done there, I think.
Yeah, definitely. I also see it that way. So hopefully academics can try to be up to date, and we can find some synergies on how to actually educate the next generation of developers for whom it will be more common to know this information. Now, I think I would like to dive into a bit more specific questions to each of the individual protocols. So in case you cannot answer, feel free to just hand over the mic to the panelists next to you. So maybe starting starting with Zama aspect, I would be interested in where do you actually see the fully homomorphic encryption solution that you are building going in the next couple of years, and also maybe outline some of the challenges along the way that you see and maybe how you try to tackle them.
So we want to make it more generally available. So that's the key thing. We want to make this stuff accessible for anyone. Performance is a big thing. In my head, the way that the landscape looks like now is that we're sailing on the sea and we're looking for these islands where it makes sense, right? Back to this question about where does the performance and the cost that this has, where does it actually make sense? It's tempting sometimes to think that this is a silver bullet that you can just throw at any given application and then it becomes more secure because now it's operating on encrypted data. I definitely don't think that's the way to go. We're still at the phase where we want to look for those islands in the ocean where this stuff makes sense. So performance is one thing we're really working on, making it more generally available, not requiring too many modifications to tools. Finding those use cases. We believe there is something there. We believe that confidentiality on the blockchain is currently missing and it's holding back some adaptation of it. So this would be one of these things of going from 0 to 1, where there's simply stuff today that you can't do, but that you can do if you have confidentiality. So I think that's the main challenges we have.
Something to add, or sounds good.
I would just want to add that out of all of the programmable crypto primitives, FAG is the closest to magic. Right? It's just like, imagine the experience of replacing a code. So think about FAG in the context of AI. It replaces like how you run AI today. Just take out whatever GPU and then you run AI with this magic stuff and everything is private. It's super, super powerful. It's also a very tough problem, right? So Zama here is leading this effort, and I think it's really amazing, right? It's kind of like our duty to tag along and try to identify these islands, right? To try to surface these use cases. They can be small, but still they're very interesting, right? Kind of like building this magic is not going to be that one day poof, there's no GPUs, only whatever FAG, ASICs, or some kind of like solution. It takes time, it takes effort, but it also takes adoption, which is our job, not just Zama.
Maybe a question to you, Omer, when it comes to actually the aspect of acceleration. Like, can you maybe provide information to the audience? Actually, how do you approach the aspect of acceleration? Because of course, building a dedicated ASIC is very challenging. So maybe if you can outline on how you actually approach it to identify the individual primitives that can be later on accelerated and the journey on how to actually optimize those in various stages.
Yeah, so when we started the company, we thought it's going to be this very traditional ASIC company. You identify some computational bottleneck, you prototype on FPGA, then you build an ASIC, and then you build the second generation and so on. ZK is a very zero knowledge, right? And post-quantum cryptography, MPC, FAG, they're all the same. Very unique problems in how you can, in the definition, like it requires a lot of compute, a lot of memory. They can like expand the times, they can shrink at other times. So super interesting design space. We started by identifying the computational bottlenecks, and that's basically what we do with every problem that we are tackling. First, let's see what we are up against. Let's run some profiling. Then we develop the tools to accelerate these primitives on just some hardware, specialized hardware. It can be AI hardware like GPUs, can be FPGAs, and can be, now we already have like ZK ASICs in the market. So it can be like a different variety of hardwares. Now, that's usually not enough. I mean, that's nice, but now we are actually looking at the entire problem end to end, and you want to move it to the to the best possible solution. And now you are much more specific to the use case you have at hand, right? Not all the time you have like data center full of hardware that you can utilize. Sometimes you are required to meet some specification of low power and cost and so on. So then we try to identify these requirements and make sure that we actually do our best to build a solution, hardware and software, that would meet these requirements.
Great. And maybe I think this is a great bridge for DC when it comes to actually building up a solution that is combining the aspects of ZK, homomorphic encryption, trusted hardware, maybe into the aspect of WorldCoin. If you can maybe a bit more elaborate on actually how did you manage to build the protocols combining all of the individual primitives that we see nicely together?
So at WorldCoin, we're very much like user-driven, right? Like we have 12 million users that have downloaded the World app, 6 million of which are verified by the orb. All the things that we're thinking of when it comes to actually putting all these protocols and applying them for something is because there's a direct demand. So the reason why we implemented SMPC for our protocol for uniqueness checks is because we are now going all around the world talking to regulators and data privacy authorities, telling them, hey, we want to do this biometric imaging, whatever, but it's privacy preserving because using cryptography, all of these things. Sometimes it's really hard to communicate all these things, but But essentially, what you're selling here is privacy, right? Like the reason why it's okay for us to onboard people and take biometric images in this hardware device that is attested and uses cryptography is because you're able to convince them that it's actually privacy preserving, right? So that's like one big use case. And it makes it much easier because now they're all worried about like Meta and all these things. They've seen all the leakages of information about users, etc. And now they want to push companies to just not keep any data. And I think this is like a narrative and trend that we should keep pushing, right? Self-sovereignty of data and all these things. When it comes to other things, right now, like all of the use cases that are centered around us is either scalability. So let's say that you can ZKify the EVM and you can scale blockchain so we can support more users. That's one use case. Digital identity, I guess, would be the biggest one when you have semaphore, right, for the proofs of personhood. You can do things like proof of passport. You can verify a signature on a passport and then you can make proofs about the information on your passport. I can prove that I'm over 18. I can prove that I'm from a specific nationality, that I don't know, that I'm not on a list of like registered bad people or whatever. Then you can do proofs about your web activity, right? I can prove to you that I have more than 100 rides on Uber or that my favorite artist is this because I've listened to 1,000 hours of their songs. You can make arbitrary attestations and you can create a cohesive sort of digital identity framework. So this is sort of like where we're heading more or less. And that's like why we rely on companies like Ingonyama and Zama and all this to essentially build the tools so that it's performant enough to the point where we can build applications that are compelling and that can bring on the next billion users to blockchains and new age, new era, privacy-preserving identity tools and so on and so forth. And yeah, that's more or less how we think about it.
Perfect. Maybe a follow-up question afterwards to Morten with respect to the scalability and usability. You have recently introduced a new approach on actually how to achieve it using the coprocessors. Maybe can you briefly mention actually the idea behind it and where do you kind of see it envisioned for the adoption?
So about a year ago, actually, at EthCC 6, we introduced what we call the FHEVM. So this idea was that as a smart contract, you now have encrypted data types and you can perform operation on these data types. However, all the processing there happened on directly on the validator. So this means that now you need beefy validators because of the sequential nature of it. There's a certain limit to what it is. So what we're talking about this week, we're presenting on Thursday, is what we call the coprocessor. So it works in the sense that on Ethereum, since we're here, we're basically doing a symbolic computation. So we're defining what computation we want to do, but without actually doing the homomorphic computation. And then we have the coprocessor on the side that kind of follows up with the actual computation. So on Ethereum, we generate a computational graph, if you will, and then on the coprocessor, we compute this computational graph. But then we keep all the ciphertext off-chain and computed by the coprocessor. The benefit of this is, of course, we can now run on Ethereum at essentially plain text speed. And by having some trust in the coprocessor, we get the same benefits as before. But it also is a good segue into saying, but then why do we trust the coprocessor? Anyone can verify this. Our encryption scheme is deterministic, so anyone can go and challenge the coprocessor. But when we're also working on combining CK with FHE, so that we have this verifiable computation. In this case, the coprocessor can prove, okay, I've done the computations correctly, you don't have to trust me at shots.
Great. Thank you very much. Maybe a question briefly to Omer with respect to the aspect of centralization and decentralization, because some of the discussion when it comes to hardware acceleration using ZK was that the aspects of actually people having ASIC that will be allowing for the speed up can actually also lead into the decentralization. To decentralization. What is the approach of Ingonyama when it comes to actually allowing it for broader set of users?
That's interesting. I actually heard like the counter argument that by producing a cheap enough like ZK hardware, ZK Sync, for example, that's like what they are aiming for, right? So right now you can run proofs on ZK Sync with GPUs, but it's coming from one vendor, right? Just let's say NVIDIA. So having another ASIC first decentralized like the vendor, so now you have at least one more. Maybe it can be few ASIC providers, and second, it kind of like makes it more decentralized in the sense that now everybody can buy an ASIC, like, and run it at home and run proofs. So I mean, I don't know. I mean, for us, we're more focused on the technology part of it, but it's definitely not necessarily like ASIC equals centralization or decentralization. I guess it's like can go in both directions.
Great. Something to add, DC?
Yeah, I mean, To that point, like, I would just like to see more hardware get into like phones and consumer hardware, like ZK hardware or cryptography enabling hardware get into regular devices. But for that, you need to get big use cases that drive that demand. Like the reason why everyone has a phone with a neural engine or like a chip that does AI really fast because it's optimized for matrix multiplications is because everyone has a Siri on their phone, or everyone has, I don't know, like Apple Intelligence or all these other like use cases that want to use like ChatGPT or whatever on the client. My call to action would be build something that is so damn useful that it just feeds like companies to make it profitable. Like it would be very profitable for them to accelerate these things. Because once there's demand, everything takes care. Like the capitalistic economies of scale get rid of the problem over time if there's enough demand for the market. So this is like the thing that would speed up decentralization the most, because now everyone would have a chip, and if there's a lot of competition and a big market to seize, then there's a lot of incentives to build multiple competitors, and hopefully it doesn't end up being like NVIDIA and AMD, where NVIDIA is like 90% of the market share. Yeah.
Great. I think with the time we have last question. So this is more like motivational aspect of providing some of your tips and your experience to new developers in the audience that might be interested to start their journey when it comes to looking into ZK, FHE, and other topics. So what will be your tips for them to dive into the details? DC, do you want to start, or whoever?
I'm happy to start. So my tips would be, find the reason for wanting to learn it. It's really hard to learn this thing unless you really care about it. So if you really don't know what programmable cryptography is, just search around the internet, ask ChatGPT, like ask things that you care about, and try and see if it fits into whatever things you care about, or try and explore. Once you get hooked, there's lots of resources. There's things like the Zero Knowledge podcast. There's things like ZK whiteboard sessions. There's an FHE.org website, I think, where you can learn everything about FHE. There's resources on MPC. There's all sorts of resources. But yeah, like I think those are like fairly available, and everyone knows how to search the internet. So I think like the thing is just find a passion or drive that sort of would use cryptography for something. Right? Like if you have a passion for privacy or scalability, then cryptography is your thing. If you want to build a consumer application that is private and proves things to people, then cryptography is your thing. So if you find that, then everything else will take care of itself.
Feel free to reach out to me on Twitter or Telegram. It's kind of like Omer Shlomovits, like my name, and just ask, and I'll be happy to help. And I guess I'm just like one case out of this concept of just reaching out to people and ask them. So I can tell you that I think the way I met Morten here many years ago was around an open source library for homomorphic encryption, and I just reached out. We just wanted to ask a question. That's the best way to do it.
Yeah, I think that's a good point. Communities, online communities, there's a few that's working on this stuff. And maybe just to add that I think the people that are working on the core tech, they are very interested in use cases. So if you come in with an application in mind, they're generally very interested to hear how do we actually want to use this. And to Omar's point, so yeah, Zama AI, if anyone is interested, we have the FHEVM and TFHERS. We have communities around that, so more than happy to help getting started.
Great. Thank you very much to the panelists, and please give one round of applause. And keep building and stay hungry. Thank you very much.
Cool. That's it for today, everybody. Thank you very much for coming. Feel free to stick around, mingle around, network, and see you tomorrow for restaking day.